Hey everyone, welcome to Spinnaker.Live. My name is Amy Smidutz. I'm the manager for resilience engineering at Netflix, and I'm here today to talk about infrastructure experimentation using Spinnaker. Most of you are at least probably familiar with Netflix. We have 183 million paid memberships in over 190 countries. And in order to deliver content to all those people in all those places, we maintain a very complex distributed system. This picture that I have up on the screen is a bit outdated, but it still gives you an example of how complex the Netflix application is. We have so many microservices, and they're all manner of patterns of traffic routing. And in order for us to operate a system of this size and complexity, it requires heavy investment in reliability and resilience practices. So today, I want to give an overview of one such practice, which is infrastructure experimentation. We use infrastructure experimentation to proactively avoid production problems by running production tests and learning about our systems. And Spinnaker plays a huge part in this. My goal for the talk today is really to introduce you to how we're experimenting using Spinnaker, so that you could think about how you could start experimenting in your own environments. And then before I get started, I just want to tell you a little bit more about what the resilience team does. We want to help Netflix engineers that are working directly on the Netflix application avoid this. We don't want our customers to see screens like this. We know that things are gonna go wrong, so we're trying to be resilient when they do, which is another way of saying we're trying to degrade gracefully when things go wrong, when we have failures. We're definitely not trying to drive out any failure. We definitely know things are gonna go wrong in the system. We're just trying to drive resiliency practices so things keep working even when there are problems. So one of the ways that the resilience team does this is to provide tools and insights that engineers can use to experiment with their application in production. And this is what I mean by infrastructure experimentation. It's really as simple as wanting engineers to build up resiliency to failure by learning and experimenting with their application. So infrastructure experimentation starts with A/B style testing using a canary strategy. And canary in and of itself is an infrastructure experiment with the main purpose of safely testing in production. Canary is a loaded term that means different things at different companies. So I'll give you a quick overview of what I mean by canary and how we use it at Netflix. Simply, it's setting up two clusters in production alongside your normal cluster. In this diagram, we have a normal production cluster. And then we have a smaller cluster that's serving new software. We call that the canary or the experiment cluster. And then we have a baseline cluster, which is also serving the same known working software as our production cluster. And the point of this particular strategy is to make sure the software change is good. So I'm just going to throw some numbers up here so you can get a feel for what this looks like in practice. We have 98 instances already in production. And then we want to deploy some new software. So we set up two new small clusters of one instance each. The actual size of the clusters can vary. It doesn't have to be a single instance, but they're always very small. We're using a very small cluster so that we can have just a small subset of traffic going to them. And this is kind of what I mean by a small subset of traffic. So using a canary pattern, we have reduced the blast radius. So by reducing the blast radius, I mean that if something goes wrong with our experiment canary, we will only affect a small number of customers for a short period of time. So while we're testing our deploy in production, because it is the most accurate way to test, we're still only subjecting a small number of customers to the change. So if something goes wrong, the blast radius will be small. We use Spinnaker for orchestration and cluster management for Canary. So Spinnaker takes care of the heavy lifting for us. It sets up these clusters, all the routing, and then it will tear everything down for us after our experiment is over. So now that we have 2 clusters that we can experiment with, we are able to measure the difference between the 2, so we can learn if our software change is behaving as expected. So by having 2 like-sized clusters, we're able to actually get metrics from each. We can look at those graphs, and then we can make a comparison and say like, hey, they look pretty much the same. It's probably fine. Let's go. And then we would proceed with a deploy. Otherwise, we'd say, whoa, these graphs are wildly different. There's a problem. Let's not push to production. Let's investigate further. So it's really about easily seeing deviations if something has gone wrong. But analysis is hard. Over the years, we started with that same manual process that I described, which requires engineers to look over all the data we're receiving and then use their own judgment to decide if it's safe to deploy to production. And not only is that tedious and causing a lot of toil, but it's also fraught with errors because we're using humans to pour through a bunch of data and then make judgments. So over time, we knew we had to improve our ability to analyze metrics automatically. So a few years ago, in conjunction with engineers at Google, we introduced the Kayenta platform. And basically what Kayenta does, it's an open source software that's available to you today. And it enables automatic canary analysis by measuring pre-configured metrics. And just to give you a few fun facts about Kayenta, Kayenta is named after a coal mine in Arizona in the Black Mesa area, which keeps up with the whole canary in the coal mine analogy. This picture is actually from my honeymoon. I took it when we were driving through Arizona so I could send it back to the team just so they could get a kick out of it. And it comes in handy ever since because we don't have a cool logo for Kayenta. So getting back to our diagram, Spinnaker can call out to Kayenta to run automatic canary analysis, which will detect when the baseline in the experiment cluster deviate enough to indicate that it's not safe to deploy. This gives our service owners confidence in that their deployment is safe. So now that we know a little about Canary, let's talk about other kinds of infrastructure experimentation that we do building on this Canary strategy. So chaos engineering, this is something that has been a part of the resilience team for a long time. And chaos is exciting, right? Just the word itself is actually exciting, maybe even a little taboo. And maybe sometimes a little scary. Maybe we all have a little too much chaos in our life right now. We can apply this same feeling to engineers that are already familiar with some chaos practices. Even if it is an exciting topic to them and they want to employ this practice and they see the value in this practice, it still is a little bit scary from time to time, especially if they already have a heavy operational load. And the reason that it can be hectic is because chaos engineering is chaotic because we are creating real world problems in production. So that means when things go wrong with chaos, alarms will go off, monitors will turn red, and of course, subsequently, your blood pressure will probably go up. So to give a little bit of history on chaos engineering, a lot of you are probably familiar with Chaos Monkey, which is one of the first, or possibly the first foray into chaos engineering for Netflix. And Chaos Monkey, while it still is in existence today and well used at Netflix, it is a blunt tool. It creates a common failure, which is that instance types sometimes disappear. And the point of that is to teach engineers to architect their systems to be resilient against disappearing instances. This was a big problem for us when we were moving from our data centers into AWS, and all of a sudden we had to deal with ephemeral instances. So that's where Chaos Monkey had its greatest value, was to very quickly teach our engineers how to fight against this particular problem and build resiliency into their systems about that. And we saw so much value in that we continued to invest in these kinds of chaos tools, which basically just cause random failures that are common in a distributed system. some of these tools ended up in what is known as Simian Army, which has been deprecated now, and all of the pieces have been pushed into other systems. But at that time, after engineers were getting used to the practices of chaos engineering and they'd seen a lot of value out of it, they also were starting to opt out. And when we were looking into that, we found that the pain of experiencing these failures was beginning to outweigh the lessons that were learned. So even though they realized that learning these patterns and building resiliency against them was a valuable thing, they were overwhelmed, and the idea that a chaos tool was going to come in and stomp on your service was just too much. And so they were starting to push back on maybe not taking part in all of the chaos tools that we were offering. So that's when chaos experimentation started. The ideas around that started to form. Chaos experimentation is a way we can perform chaos engineering with more safety and less fear. And one of the ways we do this is by marrying chaos with a canary strategy. So just to give you a little bit of an idea of what chaos engineering generally is and what chaos experimentation generally is. So chaos engineering and chaos experimentation, they both run in production. That's a very important part of chaos. If it's not in production, then it's not chaos. You want your chaos engineering and your experimentation to be automated and continuous. So these things should be happening to build up resiliency, which means that it needs to be continually happening. And we always want our chaos, whether it's engineering or experimentation, to simulate real world failures. And this is just about prioritization. So we want to make sure that whatever we're testing is something that is likely to actually happen to us. And oftentimes it's something that has actually happened to us. And that's why it's something that we continually simulate. What some of the differences are is that the chaos engineering that we were practicing using Chaos Monkey, and we still are today, and some of those other tools, they don't necessarily minimize the blast radius. So with chaos experimentation, we put a first principle towards minimizing blast radius, so that when we're experimenting, we're actually affecting as few customers as we possibly can while still getting great results. We also are using advanced monitoring. So we're not only pulling in information from Canary, but we're using other tools to let us know how things are going while the experiment is taking place, which allows us to actually implement automatic stopping. So if you do accidentally create a problem in production, we have automatic stopping in place so that we can shorten an experiment and stop it before it continues to cause problems. So in order to actually provide chaos experimentation, we realized we needed more sophisticated tooling that allows engineers to safely learn from chaos. And that's why we created CHAP. CHAP was originally named the Chaos Automation Platform, but as our tooling has grown, we've realized that it's capable of creating other kinds of infrastructure experiments that go beyond chaos. And I'll talk a little bit about that later in the talk. So CHAP, which we sort of refer to as Change Automation Platform, but we realize that that can be confusing as well. So name is still up in the air. But CHAP, the platform, enables us to run infrastructure experiments like chaos experiments by pulling together other platforms like Spinnaker and Kayenta, and actually a whole bunch more. And again, chaos experimentation is a different kind of chaos engineering because it's more about studying the problem than it is simply reacting to it. Since CHAP enables engineers to use chaos experimentation in a safer way, it makes chaos engineering less scary. So it's really attacking that problem of engineers being afraid to engage in chaos engineering, or chaos engineering is causing way too many problems for engineers to react to, and creates a situation where you can still get all the benefits from chaos engineering, but in a much safer and less scary way. And along with chaos experimentation as a change in mind frame, we also are using CHAP to run more complex experiments. So we're looking to affect and learn from resiliency to downstream service failures. We want to make sure fallbacks are behaving as expected, and we're looking for systematic weaknesses. So I really want to give you an example of what we mean by a chaos experiment. So I'm going to zoom into one of these things. Do my fallbacks work as expected? This is a common experiment that non-critical service owners use to verify their service really is non-critical. So let's walk through this test to get a quick view of some of the mechanics. And I'll just go ahead and start by explaining what a fallback is in case you're unfamiliar. So anyone that has ever watched Netflix before is probably familiar with this screen or something similar. When Netflix is working normally, you'll see a screen that looks just like this. The play button is our critical functionality. Pushing this allows for playback to begin. We want everything on the screen to be available to a user, but if some of it isn't for a short period of time, that's fine. So when a customer pushes the button, we want them to see this. The big N shows up, you hear the bong, and then joy commences. We do not want them to see this or any other kind of UI-related error. And basically, all of our effort is to try to degrade gracefully so that when errors pop up that are avoidable, instead of seeing this screen, you would instead see degraded functionality on that first screen. There are a ton of items on the screen, and many of them are not critical to be able to actually play an episode. So here's an example. This is called a badge, and it just lets you know something about the show. This is a badge that lets you know that it's a top 10 show, and these buttons are for our rating system. So these and many other things on the page are all separate microservices that make up the Netflix application UI, and many of them are not critical. So to talk a little bit about the experiment we're going to run, I created a simple and largely inaccurate diagram as an example. All the red boxes are critical, which means they are required for playback to work, and all the blue are non-critical. Non-critical services use strategies like fallbacks, which means if a critical service reaches out to a non-critical service that is unable to communicate, we'll send fallback data rather than error. This allows some elements of the UI to be unavailable rather than causing the UI to crash or playback to fail. But how can we test that the fallback actually works in production? We could use an issue, we could actually cause an issue in production. We could take down that service and see what happens and just hope that our fallback actually works. But if our fallback isn't working correctly, we could cause an impact to the service. This would cause a problem for all Netflix customers in the region that we performed the test. So this is where minimizing the blast radius comes in, and also where the canary strategy comes in. So by creating those two small clusters that are exact replicas of the service we want to test, just like the deployment canaries, they're stood up in production, and we can send a small amount of customers to each of these clusters, and that will reduce the blast radius. So as we experiment, if there is a problem, it will only affect a small amount of our users. So in this scenario, we cause communication failures between the experiment cluster and the service calling it, and while the baseline just continues to work as normal. This will trigger our fallback, which, if working correctly, will send dummy data back. And if our experiment fails, the customers that are in that experiment will not be able to start playback. If the experiment passes, playback will work as expected. And regardless of the experiment outcome, all customers that are not in the experiment will continue to have fully operational service. So we are experimenting with real people. And even though all the tests that we run, we assume will work, we don't ever run a test that we assume won't, because again, we're testing with real people. Even though our hypothesis is always positive, experiments do fail often. That's why it's important to continuously test. So even if it is a small number of people in our experiment, we don't want to cause them problems for too long. These are our actual customers and we love them. So we don't ever want to cause them pain if we don't have to. So CHAP measures real-time analytics using a platform called Mantis. Mantis is from Netflix. It's also an open source technology, and it's a stream processing platform that allows us to get real-time operational insights. We use this to measure metrics from the baseline in the experiment cluster, which allows us to measure a lot of metrics while running an experiment. But one of our key performance indicators is stream starts per second, or SBS. This metric most closely aligns with customers not being able to start playback. So this allows us to detect if there's an issue within 5 minutes. And this is what allows us to be able to safely experiment with a small part of the population in production. So to give you an example, again, we're using our trusty canary strategy to test if there's a deviation. The blue line is the baseline, and the red is the experiment. We even boost this signal by using what we call a sticky canary, which means we tag the population of customers that are routed in the start of the experiment, so they will always be routed back to our experiment until it ends. If SBS for the experiment cluster deviates from the baseline cluster, we can automatically detect the problem quickly, and CHAP will automatically stop the experiment. So this is important because this is our stopping mechanism, and this is what I meant by advanced metrics. Because we're using advanced metrics and we have a key performance indicator, we're able to actually put a stop to an experiment before it causes too much harm to our customers. And since we're able to do this, we can actually stop an experiment soon enough that it's unlikely that a customer is going to get so upset that they wander off to use a different service or leave our service altogether. In addition to the real-time metrics that we're getting from Mantis, we also run a full analysis using a canary analysis platform, Kayenta, at the end of an experiment, so service owners can get additional information about their service. And this is just an example canary report to give you a high-level idea of what you can see in this kind of report. So Kayenta allows us to run standard metrics plus anything else the service owner wants to keep an eye on, including metrics that are specific to their app. And so far I've talked about how Spinnaker helps us orchestrate experiments using Canary and connecting those experiments with Canary analysis using Kayenta, but we also use it to schedule continuous experimentation. Because again, that's a really important part of infrastructure experimentation. So here's an example of a custom stage that we created. So we've added several custom stages to Spinnaker so engineers can configure an experiment right from Spinnaker and set up pipelines that include chaos experiments. So this means that if they want to have any particular experiment that we offer as part of their deployment pipeline, they can. If they want it as a separate pipeline, they can. But the important thing is that they have tools to enable running these things on a regular basis. So I mentioned in the beginning that chaos is not the only infrastructure experiment that we run using CHAP. So using CHAP components, we're able to orchestrate a production load test. And this experiment is called Squeeze. So this allows us to safely perform an accurate load test in production. And engineers generally use this to get accurate measurements of their optimum requests per second. They can also use this if they want to test changes to their service, such as making a change to an instance type family. Spinnaker helps engineers run Squeeze experiments regularly, which allows them to see performance regressions over time or improvements, as is the case in this chart. But the important thing is that we can actually see the changes as we run squeezes over time. A lot of people are running these daily, some of them less frequently, some of them more frequently as they're trying to investigate problems. But this is just another experiment type that we offer for our customers. So again, the takeaway here is that Spinnaker, Canary, and Kayenta can provide powerful insights to your deployments and other infrastructure experiments. So while CHAP is not open source, Spinnaker and Kayenta are, so you can get started with Canary as part of your deployment pipelines right now, and then add to those tools over time. So that's it. Thank you all for sticking with me. I hope everyone is safe and sound. And please connect with me. This is a community and I would love to get to know you. I'd love to talk more about these things. I'd love to hear what you're doing with your own infrastructure experimentation. And also if you love testing in production, if you love reliability, or if you're just passionate about making your fellow engineers successful, please reach out to me. The resilience team is hiring and I definitely want to talk to you. Thank you all, and I hope you enjoy the rest of Spinnaker Live.